Whether sitting on the ramp, being under tow, or in flight, the center of gravity and its limitations play an important role in aviation safety. So just what is this all about? And what's the meaning of percent of Mach anyway? Well, let's take a little time to do a little primer so that you can better understand the importance of your center of gravity and its computations. First, let's begin with a little review of the aircraft's roll, pitch, and yaw axes, and how center of gravity and the various other forces in flight like thrust, drag, and lift all have an impact on how the aircraft flies. First, forgive my use of an Airbus since we're talking Boeing here, but this is a good graphic to illustrate. Notice that the roll axis, which is also the longitudinal axis, goes directly through the center of the aircraft from front to tail. The aircraft, when it rolls, induced by the ailerons, rolls about this axis. Then the lateral axis, also known as the pitch axis, is what is affected when we pull on the elevator or push down on the elevator or we change the pitch trim. Finally, we have the yaw axis, which is vertical, and this of course is affected by the rudder and or the yaw damper in flight. What is not illustrated by this picture is the fact that all of these axes run through the center of gravity. So when we roll the aircraft, we pitch the aircraft, or we yaw it, it actually moves or pivots around the current location of the CG. The center of gravity is exactly that. It is the concentrated location of all the mass in the aircraft, and if we were to hang the aircraft from a cable, it would balance exactly at the center of gravity point. When an aircraft has a forward center of gravity, it is more stable. In other words, it resists vertical displacement of the nose. When an aircraft is loaded with an aft center of gravity, on the other hand, it becomes less stable and more sensitive to pitch inputs. In fact, if it is loaded far enough aft, it becomes very unsafe. There are two types of stability that we're interested in. One is static stability, the other is dynamic stability. The three types of stability in static stability are illustrated well in this graphic. We have positive stability, neutral stability, and negative stability. An aircraft with positive static stability will tend to return to its previous dynamic trim point. An aircraft with neutral static stability, on the other hand, when the nose is displaced from its trim point, will tend, when the controls are released, to just stay in the current attitude that it's in. The worst case scenario is an aircraft which is displaying negative static stability, and in this case, when the nose is displaced from its trim point, the nose continues to diverge, either increasing in pitch attitude or decreasing in pitch attitude, which of course you could probably imagine is very dangerous. Dynamic stability is what occurs after an aircraft with positive static stability has a displacement of the nose either up or down. What we would like to see is what happens in example A here, where the oscillations, what we call phugoid oscillations, get smaller and smaller until the aircraft returns to its previous trim point. Now, the further aft that we load the aircraft's center of gravity, the conditions tend to progressively move from A, positive static and positive dynamic stability, to B, neutral, and then to C, negative. An in-flight example of this would be I have an aircraft flying in level flight at 250 knots. I displace the nose up 10 degrees and then release the stick. The aircraft, if it's in positive stability, will go through a series of vertical oscillations, airspeed decreasing and increasing as the nose moves up and down, and eventually return to 250 knots in level flight at the altitude that it originally started from. In the case of example C, however, the aircraft may continue to oscillate further and further from the altitude and airspeed at which it started, ultimately maybe even resulting in a crash. This stability is the product of the relationship between the aerodynamic center of the wing, otherwise known as the 25% of Mach location, the center of gravity, and the neutral point. And the neutral point is something that is not shown on this diagram. Essentially, it is the fulcrum point where all the forces acting on the aircraft in flight come together as a fulcrum. Thrust, its pitching moment from thrust, lift, the down force of the tail, any pitching moments caused by the fuselage, all come together at this point we call the neutral point. If the center of gravity is far enough aft that it's sitting directly on top of the neutral point, the aircraft will exhibit neutral dynamic stability. If it moves further aft, that's when the aircraft starts to show negative dynamic stability. Now, Boeing doesn't tell us exactly where this neutral point is located. Instead, what they do is they give us the center of gravity envelope, define its aftmost limit, and tell us not to operate the aircraft behind that limit. In this particular case, the aftmost limit possible is 36% of Mach. Now that brings us to our final subject in this tutorial. What is Mach? Mean Aerodynamic Chord. And what does it have to do with center of gravity, and why is it so important in the first place? When we consider a straight-wing aircraft, its aerodynamic center, or center of lift, is in a consistent point 25% aft of the leading edge of the wing. However, it gets more complicated when we look at a swept-wing aircraft. As you can see by the illustration, the swept-wing aircraft, its aerodynamic center on any given point on the wing moves aft due to the wing sweep. This makes determining where we need to put the center of gravity in relationship to the aircraft much more difficult, because where is the center of lift anyway? On a straight-wing aircraft, we merely measure the distance from the front of the wing to the trailing edge of the wing, and that is the length of the chord. The quarter chord, or aerodynamic center as it is also known, is very easy to find in this case. However, with the swept-wing aircraft, the quarter chord moves aft along with the sweep and taper of the wing. What we need to do is mathematically convert this swept wing to a straight wing, and that'll solve our problem. Fortunately, the engineers at Boeing have done this for us, and the leading edge of Mach is located 627.1 inches behind the reference point for center of gravity purposes, and Mach is a total of 155.8 inches long. Interestingly, you'll note by this diagram that the leading edge of Mach does not start at the wing root, and it does not end at the trailing edge of the wingtip. It's an average. The basic center of gravity formula locates the CG in inches aft of the reference point near the nose of the aircraft normally. Once we know the mean aerodynamic chord, where it begins and where it ends, we can then use a formula to convert the center of gravity to a CG in percent Mach. Well, I hope you enjoyed this presentation. I hope I didn't confuse you too much with my final explanation of how weight and balance works. We didn't get into the formulas. We don't need to do that. But at least I hope now you have a basic understanding of how center of gravity and the mean aerodynamic chord are related to each other.